in the grand scheme of things, right? You know, of course, we're in the last 2 weeks of classes after Thanksgiving. So I apologize that we have next week, right on the tail of the midterms that we had a week ago. Uh, yeah, a week and a half ago, we have the finals. So, but anyway, that's kind of occasioned by the scheduling. So anyway, but they're actually, at least we're conforming to the Senate rules, which are there to protect you, and that is that nothing in the final week of classes could be worth more than 10% of the grade. So don't know whether that's good or bad. They're tests and you're doing them, and so you might want to get fair measure for them, but you get half of what the other ones are worth just because of that ruling. I think it's a good rule to have. Otherwise, everyone loads up stuff in the week before finals instead of finals week for whatever reason. So these ones aren't in the Pollock Testing Center. What's the thoughts about Pollock Testing Center? Good, bad, indifferent? No one to say anything? You don't want to compromise? You kind of guess, what does he think about it? What does he want me to say? Because it's independent. I can think of ways to game the system. If I was gaming the system, I could game Pollock as well, I think. So yeah, so I think it's an imperfect world. I put that in the first time this year because someone very ardently in their SRTEs, which you don't have anymore, they call them something else, was annoyed about the fact that there was some end runs going on for doing it all just online in the comfort of people's homes. So that's why that was done. So I'm curious to maybe hear confidentially what people say in whatever they call the SRTEs now. Anyway, so we're in the home run. This will be the last week of classes, week 13 in terms of topics out of 15 weeks of classes in a semester, as you know. And so the final 4 weeks and 3 topics have been pipe flow for 10 and 11 and pipe networks, and external flows for wind turbines and lift and drag around bodies and cars, etc. And finally, open channel flows, which seem perhaps less relevant to the disciplines that you find yourselves in compared to the 2 that preceded this. And so the essence of open channel flows is that there is no pressure drive, as there is in air pressure around turbine blades and fluid pressure in pipes and well bores. But all of the drive that's driving flow is gravity. And so this, you could imagine, is an elevated flow upstream left of this plume. And so the one interesting thing is it's not a confined flow within a pipe, so it actually can rearrange its cross-section of flow to be either a fast flow that's very shallow on the left-hand side, or a slower flow that's deeper on the right-hand side, because we know that if you take a section across it anywhere, it has to be the same volumetric flow rate. And so this free surface allows it to rearrange itself in some way. And that's kind of the essence of open channel flows. And so I think the interesting thing about these, and we've made this point before as well, is if you're surfing West Virginia, as they would say, then many of the things that we've talked about have been related to balancing gravity with forces. And so for hailstones falling down in thunderclouds, drag on the hailstone is balanced against gravity, which is the motive which is pulling it down. And it's not so different here in surfing West Virginia. Gravity is driving you down the face of the wave, but the water's flowing past you and providing some kind of friction on the bottom of the boat, perhaps viscous forces acting on the bottom of the boat. It would be the same as snowboarding, going down a hill, using gravity to go downhill, and friction acts against the base of your snowboard and also the air resistance against your body. And so that's kind of what we're dealing with. And so we're balancing those forces. And so more interesting, I think, are some of these. New River, of course, not very far from here in West Virginia. Big rivers in West Virginia. I guess probably four hours drive from here. New River and the Gauley. And it was interesting to see what people can do on these waves. Anyone here? Kayak? Boat? Yeah, do? Hard shell? Or oh yeah, might be kind of a cool place to do it. Yeah. So lots of, I guess, seasonal rivers here, and actually the New and the Gauley in West Virginia are all dammed rivers, which are horrible for fishermen and free-flowing fisheries, but perhaps great for boaters because you get, I guess I usually cut the sound off, don't I? You usually get scheduled releases. So used to be a boating club in town that used to be a nice Penn State outing club, and the local townies were all in actually a very tight-knit community before the university decided to take over and have PSOC really owned for students. And so that kind of fell apart. But it was a nice mix because the local people were the people with cars, and you need cars to transport boats somewhere if you're going to use them typically. And so it's just a nice melding between cross generations and just continuity as well. People in town stay in town for 40 years, and students are ephemeral, come in for 4 years and are gone, and et cetera, et cetera. So it gave some continuity to the activities. So you can rent kayaks. Actually, some of the people, Garrett Ziegler, the guy who's the TA, undergraduate TA for this class, who was in this class last year, and his friend also from this class rented kayaks to go boating. I don't remember where. Little Juniata in Spruce Creek is a local river that keeps water all year round. Spruce Creek is a little tributary that runs into it that has a very illustrious rod and gun club that Jimmy Carter, in the news these days because of Rosalind Carter's death, used to come locally and fish. Clinton, I guess it was a Democrat-owned rod and gun club. They used to come and fish there in a high-quality fishery that coexists with a big-time factory farm for dairy, which has lots of poop that gets respread on the valley, on that valley of Spruce Creek, but I guess is monitored well enough that it doesn't do anything either to the quality of the fishery or to the water wells that are present in that as well. So anyway, so kayaking West Virginia. I guess we're over that. And there was another one here. What else is this? So paper. We don't want that. So so that's our activities for today. So what we'll talk about is this behavior where, unlike being constrained as previous, constrained flow within a pipe, or I guess the flow was constrained in an infinite medium before. If it's flowing past a wing, it fills up the full section from here to infinity. But here, flows definitely can reorganize themselves in a certain way. And actually, I did take this. I think I have it on my desktop. Where is it? I guess it's here. See if this works. Hopefully fine. So this was taken a month ago in Chengdu, in western China. Big river running through the city. Not sure what it is, but again, you see this. We saw a hydraulic jump before, and so you see this flow organizing itself as a relatively shallow but quite fast flow in this area down here, and all of a sudden it breaks into some other flow downstream of this. And so making the point that the volumetric flow rates at any section across here, upstream or downstream, have to be the same because of continuity, but it can reorganize itself in some way, and we have to understand exactly how it can do that, either as a fast-flowing shallow flow or a more slowly flowing deeper flow further downstream. And so that's kind of our tasks in trying to understand this. So that goes. So I guess I can do that. So let me get this going. So that's our plan for today. I guess so excited I didn't turn my pad on. So I thought that maybe we would perhaps recap some of the things that we've talked about in the last couple of weeks and put everything in the same format. And so we'll talk about these classifications for flow, for open channel flows, where we have a free surface. And we'll find that they can be uniform flows or gradually varying flows or rapidly varying flows. That's what that classification is. We can define things in terms of hydraulic radius. We know that when we talked about Reynolds numbers, we talked about a characteristic length, which was a diameter. And we can define that, I guess we already have defined it as a equivalent hydraulic diameter for pipe flows, for non-circular section pipe flows. And then probably today we'll finish with talking about uniform flows. And uniform flows is just a simple demarcation to say that the depth of flow as you go from upstream to downstream doesn't change. Y is the depth of the flow, and we can accommodate that. So those are the things we'll talk about today. But before we do that, let's just recap of kind of where we are with all of this. And let's do something in a nicer color than that. And so we talked about a bunch of flows. I guess I didn't change it. And I think you've seen this before, but it kind of cements the ideas of what we might talk about. And so in pipe flow, we certainly talked about the Moody diagram, where we had Reynolds number, which was a velocity, a density, a characteristic length, and a viscosity. And we had what we called a friction factor. And the characteristic behavior that we saw looked something like this, that you messed around with. And I'll do this just because this will save us some time as we draw multiple diagrams on top of each other, which start looking the same as each other, and which we will continue when we talk today. Again, Reynolds number. I guess this was something like coefficient of drag, right? So this was laminar flow. This was for circular pipes. The flow is internal, and it has some velocity, average velocity as you're going downstream. And if we write out Bernoulli and we look at the terms that don't disappear if we're looking at just flow down a pipe, so upstream to downstream, if the cross-sectional areas don't change, then the upstream and downstream velocities don't change. If it's a horizontal pipe, the elevation doesn't change. Then we have that the pump losses equal to the sum of the head losses in the system. Bless you. Head losses we can define in a couple of different ways in terms of the friction factor, length over diameter, and v squared over 2g. Or, I guess, equivalently, some kind of loss coefficient times v squared over 2g. I guess here, highlighting this because this is the case. And if we look at the pressure that's upstream and the pressure that's downstream, then we can always merely write this as P1 minus P2, which is a delta P divided by a unit weight. If we don't have a pump in the system, is just equal to the sum of head losses, which is equal to friction factor, length over diameter, v squared over 2g. And I guess we've also talked about, in terms of dimensional analysis, we've talked about geometric similitude. I can never remember whether the second one is dynamic or kinematic. I think it's kinematic. So this is, geometry of the model equals the geometry of the prototype. This is the Reynolds number of the model equals the Reynolds number of the prototype. It's easier to draw on here, on the open channel flow figure, that what that means is that the Reynolds numbers are so that if you look at the flow field, then laminar flow is this creeping flow. Oops, not that creeping. And as opposed to being this. This is 2000, something like that. This is some coefficient over Reynolds number, typically 96 for circular pipe, right? And if we're doing this, we have something like this. And this is turbulent, and this is laminar. And because this is a function of Reynolds number, then we know that flows on this side is that CD or F are proportional to 1 over viscosity. Actually, proportional viscosity, actually, isn't it? Because it's 1 over Reynolds number. Reynolds number is 1 over viscosity. So this is proportional to viscosity. And here, friction factor or equivalent of coefficient of drag are proportional to density. And I suppose if there is such a symbol, not proportional to viscosity and not proportional to density. So the two regimes offer different kinds of behaviors. And so we know here that this is also a function of increasing roughness. So E over equivalent hydraulic diameter. So this is a big roughness, and this is a small roughness. And so it just means that when we use these to calculate things like the velocities of flow, then we end up with direct proportionality here and a v-squared proportionality here that we solve for. It happens in both of these cases, and we solve the equations slightly differently by balancing the pressure that's driving flow, in this case from upstream to downstream. I guess the analog in this system would be, we've drawn this before, is that the flow that occurs goes around this. And I don't need to perhaps belabor the point about that. So this is pressure upstream, pressure downstream, etc. And so what did we get? We got that coefficient of drag is equal to some drag force divided by half times rho times velocity squared times characteristic dimension squared, an area. And so this happens to be the frontal area. This happens to be the force that we have to apply to resist it. And if we know what the value of D is, again, this is coefficient of drag divided by Reynolds number. I think 22, or is it 24? 24, I guess, for a sphere. And in this regime, it's proportional to viscosity. In this regime, it's proportional to density. And we explain that by the fact that it's not the drag that, so this is the shear force that goes around here, which is causing this drag in this particular case. And this is the frontal pressure that's applied here, that is the the stagnation, so the pressure one is the stagnation pressure that develops here, which is why it's proportional to density rather than viscosity. So that's kind of where where we are so far. And so the next thing to chat about is open channel flows. And so not surprisingly, because I've done this, the figures turned out to be kind of the same. But we don't reference them the same way because we have the same behavior as before. The characteristic that defines the drag is called the Manning coefficient. Which is lowercase n. And the behavior would be similar. So this is values of, if you like, channel roughness. So if you have a smooth channel, if you have a channel made of glass versus a channel made of concrete versus a channel made of weeds, then this would be rough and this would be smooth. And so this would be values of Manning coefficient, which go from small to large. And as a continuation of this, this happens to be a Reynolds number, which is also defined in terms of a velocity, a density, and a hydraulic radius, and viscosity. And what we'll find is that this regime really doesn't exist for open channel flows because they're all turbulent. And this because of the fact that hydraulic radius and hydraulic diameter are related as 4 to 1, not 2 to 1. This ends up being a Reynolds number of 500. And the region which we always find ourselves is always this turbulent regime. So that's kind of where we're going with this. And so we expect in this turbulent regime, again, that viscosity doesn't play a role in the drag that we have in our system, but it's all a function of the density, because we know that as we increase in Reynolds number, as the velocity in our channel increases, the value of n doesn't change because this is a horizontal graph. If we go from being a smooth channel in the California aqueduct, taking all of Colorado's water and sending it to LA, versus flowing down a weedy channel, which is just the banks of a river in full spate, which is overbank, then we just change the value of this coefficient. But as we increase Reynolds number, it doesn't make any difference to where we're going. So that's kind of where we're going with this. So this is open channel. Flows. And as I say, perhaps of less relevance to your disciplines than the other two, but nonetheless important. So a few orchestrated words, I guess, trying to make the point here. So this is exactly what we're talking about. So you could think about flow within a pipe, but it would be open channel flow if it wasn't completely filling the section. Because the one thing that we have that's a free parameter is the depth of flow. We can't absolutely drive flow with pressure in this case, as perhaps you can see here. If you have an upstream pressure and a downstream pressure, it'll just tend to flow in the air above it because it's much less viscous, much more efficient, and you wouldn't be able to maintain the pressure differential by flowing the fluid. And so the fact that it only partly fills the section, even though it's in a pipe, means that it's an open channel flow rather than a pipe flow. If you looked at the distribution of pressure below the surface, no surprise, when we looked at Bernoulli, you'd see that the pressure difference is just a linear one, just like going down in a static swimming pool. I guess if it was going around a curve, it would have some different format to it, as we know from looking at Bernoulli and centrifugal flows and going over a hump in a car with a the analog we talked about having water in a beaker. But if it's flowing and the section isn't changing, it would just be hydrostatic as it goes downstream. If we want to have similitude, and I guess I didn't finish my thought before finishing this, perhaps I should do. Third would be dynamic. And that is that the Euler numbers are equivalent between the prototype and the model. And so those are the three things that also conform if we're looking at open channel flow. I just didn't finish that thought. So we want to make sure that we're the same Reynolds number. We say it doesn't matter so much because we're almost always turbulent. We haven't proved that yet, but we will in a moment. The other thing that's important to us, which we haven't revisited since maybe our second class, is that we can look at the velocity of the celerity wave. And so the celerity wave is just a square root of gravity times the depth of flow. And this is the rate at which a ripple travels or a tsunami travels across an ocean basin, or which a ripple comes from throwing a stone in a lake. It travels at this particular velocity. And if the flow within the river is given by this term here, then when this number is equal to 1, then the flow is traveling exactly at the velocity of the celerity wave. And that has implications for the regime, because if you think about it, there's some information that you can imagine having to be transmitted from downstream. So we saw this hydraulic jump where we go from a shallow flow at high velocity to a less fast flow at a deeper velocity. How does it know what's going on downstream? Well, it can send information upstream, and that information will be traveled at the velocity of the celerity wave. And so something that's done quite often, or it used to be, perhaps there are more sophisticated ways now, is in drilling. If you want to send information from monitoring behavior at the drill bit, you can send it as pressure pulses in the mud up to the surface. And of course that travels at the speed of sound in mud, not the celerity wave. But it's a way of being able to get information from what's going at the bit, how hot is the bit, how much torque is being applied at the bit, and to be able to get that up to the drill deck to be able to inform what's going on. So you could think of that as being a similar way of sending information by tapping it out on the surface of the water, almost like drums, sending information by drums. We happen to define Reynolds number in terms of the diameter. And if we define the diameter in terms of the relationship between hydraulic radius and hydraulic diameter, I don't know quite kind of why this is, but it is, then it's done as the hydraulic diameter is 4 times the hydraulic radius, which means that if you measure Reynolds number in terms of the hydraulic radius rather than diameter that I put up here, so maybe this is hydraulic radius, then the fact that this ends up being a 4, 2,000 divided by 4 is 500. And so if you look at open channel flows, then this demarcation between laminar and turbulent occurs at this mark here. So that's the reason for that slightly different threshold. But we're always to the right of that and don't have to worry about it. And you can prove it to yourself just by looking at whether we are above that threshold for any reasonable river. So if you take some numbers for a channel which is 10 feet wide, 2 feet a second, it's actually a ditch really, isn't it? A foot, it'd be barely up to your kneecaps if you're standing in that. And you look at the Reynolds number for that as being equal to, the hydraulic radius is 10. So the hydraulic radius is equal to the area, which is 10 times 1, divided by the perimeter, wetted perimeter, which is 1 foot by 10 feet by 1 feet. So this is 10 feet, 1 foot, and 1 foot, which is this. This is the velocity, hydraulic radius, density, and viscosity. You end up with a number which is bigger than 500 for sure. And so the fact that even for a modest flow we're in this turbulent regime means that we're always sitting on this side of the curve, which is always given by n equals 0.01, n equals 0.1. And so if we're here, we just need to know what the Manning coefficient is that describes flow. So, classification. We said we'd classify things. These terms here refer to uniform flows, gradually varying flows, and rapidly varying flows. And I guess each of those, as I stated them, are in order of increasing deviation from being a uniform flow. So a uniform flow is that as you're upstream, the depth of flow here compared to the depth of flow here doesn't change as it goes from upstream to downstream. Gradually varying flow means that it's slightly different, maybe deeper upstream than downstream. And a rapidly varying flow means that there's a big change between it going from upstream to downstream. So that's the most uniform is the uniform flow. The next up from that is gradually changing, and then rapidly changing is more extreme as you go. And so by definition of that, if you state it mathematically, the change in depth as you go downstream in the x direction is that the depth doesn't change. Written mathematically, that's just what that is. A gradually varying flow, it's much less than 1, and a rapidly varying flow, it's different. So anyway, we'll deal with those in due course. Steady versus unsteady, we'll only deal with steady flows in our case. So each of these are steady flows. If you take a snapshot now, come back to this picture, take a snapshot 10 minutes later, this would be exactly the same profile with the same velocity distribution as you go downstream. It isn't the same as you travel along in a boat, as you see this, but it is for a static observer. So we're always looking at no change with time. And so examples of non-steady things, if you have a dam break on you, changing rainfall as a hydrograph, tidal bores in rivers would be different from that, and of course tsunamis are a transitory wave as well. So what we'll do is we'll deal with uniform flows today, and we'll talk about gradually varying flows tomorrow, Wednesday. And so the definition of this and the difference between them is given by these. The only motivation for flow is given by gravity. So it's the orientation or the inclination of the bed which provides that gravity. The slope of the bed is given by the change, I suppose, in z as a function of x. So in other words, I guess this would be this. I think we use L, but we can use this as well. So this is the motivation for flow. And for uniform flow, what we would presume is that since the upstream depth and the downstream depth, you could think of them being perpendicular to this bed, or you could think of them being vertical. The fact is that this inclination is so shallow that both of them are basically the same. You don't have to worry about whether it's normal to the bed or not. But if the depth upstream and downstream are the same, then the slope of this surface, of the water surface, has to be the same as this. And you know that when we talked about pipe flows, we talked about a hydraulic grade line and an energy grade line. And the difference between the hydraulic grade line and the energy grade line was just v squared over 2g. Since the depth of flow here is the same as the depth of flow here, the velocity has to be the same, and so they all have to be parallel to each other. And so the slope of the energy grade line, the slope of the water surface, and the slope of the bed are all the same as each other. If we look at non-varying flows, which would be gradually varying flows, and these would be uniform flows, then you can see that we violate that. There's no requirement that the depth stays the same as you go downstream. And so there's no requirement. The slope of the water surface is the same as the bed flow. So these hold that for the slopes of the water surface, the energy and the bed have to be the same. Not so for gradually varying flows. I guess the other thing that we will assume is that there's no viscous loss or the viscous loss is countered by the gravity drive. So the amount of potential energy we lose as we go downstream is exactly countered by the upstream. You could think of it as a viscous force. It's not really a viscous force acting upstream, which exactly counters the change in potential as you go from this point here to a lower elevation here. And this is applied on the perimeter of the flow. I guess the other thing that we can think of is if we think of the cross-section of flow, if we draw this in perspective, that's not too bad, is it? Is that we have a perimeter which would look like this. If I can do it properly. So this length is the perimeter. I'm going to do this. You've seen this before, haven't you? I don't know what color this is supposed to be. That doesn't look like it's going to work. I thought this, that's the wrong one. That's the right one. So this is the area. Pretty good. So the area of flow is this, with a free surface on here. And so along this perimeter, this shear stress is applied, and it resists this flow. And of course, this shear stress is applied all the way across this perimeter. And so the wetted perimeter is what is important to us, which is kind of shown by this contour here. This is the same as our P, and the A is within here. And we also make some assumptions about this behavior. Don't worry about this equation for now. So the balance between shear stress and gravity is what controls the rate at which it will flow downstream. A bit like balance between drag on the skydiver and gravity as his person's weight pulling them downstream. The other assumption that we'll make is that the flow across the section is kind of uniform. We did it for pipe flow, and so we're thinking about, if we think about this average flow here, given by this, the area under this curve, we can rewrite as an equivalent velocity, which I suppose would look like, if I drew it out, I won't overprint it, it would look like this. So we're just retreading it. And so the area that we had under it covered in yellow here would be exactly the same area that we have under this curve. That's all we're saying. So we have some kind of average velocity, which we'll call V prime, which is the same as the average velocity we talk in pipe flow. We make exactly the same assumption. You could imagine that if you have shear stresses acting at the edge of this, the flow in the middle of the pipe or in the middle of the flow channel would be fastest. You could see it. Could you see it on this thing that we looked at before? Bless you. Could almost see it, right? If you look at the profile of this, oh, geez, what am I doing? Not the red one. Green one. If you look as it goes downstream, bless you, oh, geez, is that you can see right here that this is further upstream, retarded a little bit in terms of its location. And as you look here, you see this curve here, which is bringing it. That's just the fact. It's probably getting more shallow at the edges, but it's not super shallow here. And it's just drag that's on the side of this that actually pulls it back. So those effects do actually exist in channels, but we choose to ignore them because they're not huge effects, and we can get away with ignoring it. And so we deal with that. And so here's the the math that we need to do to be able to deal with this. So this is for uniform flows. And so our idea here is to look at momentum balance. You'll remember many moons ago that we wrote F equals ma as this. This is conservation of momentum. That the sum of forces in the x direction, this is a velocity in the x direction, this is just equal to F equals ma, nothing different from that. And so this is a mass rate of flow, so there's a velocity in here and there's a velocity in here. So you remember that v squared over 2g is really an acceleration term as you're going downstream. And that's what this is. This here, I think, is a mass flow rate. Bless you. Geez, everyone, stay away from me. This is mass flow rate term here, and this is a velocity term here between upstream and downstream. And of course, if we're making the proviso that the upstream velocity in this kind of free body diagram, we've isolated a block of water. We have the velocity upstream, not the pressure, but the velocity upstream and the velocity downstream. If they are both in Cartesian coordinates the same magnitudes, then they subtract from each other. So this term has to be 0. The mass flow rate is not equal to 0, but this term will be equal to 0. And I guess if we are summing the forces in this, then we'd know that if we drew the hydrostatic pressure distribution upstream, which is forces now, not these are pressures acting on the upstream block, then the sum of those would be our what we've called FR, right? This would be our resultant force. We'd have exactly the same behavior acting in the downstream location. So F2 would be acting opposite it, and that would be, these would be pressures. So F2 would be the resultant acting upstream, this would be the resultant acting downstream, and so by definition these forces here would equal 0. But we have some other forces acting in the system. The first is that we have a shear stress, and you can see it here. This shear stress here is times perimeter times length. And so if I draw out this diagram, kind of like it is here, then the perimeter area is going to be my yellow. I must have been going to art classes over the break. Be on the back side of this, right? So the perimeter would be this length here. This length here would be the length. And so this is the wetted area times the shear stress. So that's an area times the shear stress, just like is dragging on the side of a pipe. So this is the force that's acting upstream, and the force that's acting downstream is just the weight of the water and its component acting parallel to this bed, which if this is W, which is unit weight times the cross-sectional area of this, so W equals the unit is equal to rho g times the area times the length, right? Area times length is just the volume of this component, so this is the volume. This is also unit weight area times length. And so we want the component of it which is acting opposite this shear stress, and that's if this bed is inclined at some small angle theta, then that's W sine theta, this component here. W cosine theta is the weight. And so these are just acting opposite to each other. So a long explanation for a simple outcome, and that is that we end up with this expression here. So just rearranging this, noting the fact that, well, just rearranging it. I guess since we said that the inclination of these beds are quite shallow, then if that's the case, then theta is small, and so the sine of the angle is pretty much the same as the tangent of the angle, which is same as the angle itself. So this is just equal to delta z over L, as we defined before. Delta z is just the height drop as you go along a unit length of this channel. And so we can substitute that into here, substitute this for this. And so from that, this relationship here, we can make the substitutions for W, which we have here, and we end up with this. And if we know that area over perimeter is some function of a hydraulic radius, we end up with the length over length. We end up with the unit weight divided by the gradient, just by making these two substitutions, that hydraulic radius is area over perimeter. Then we have this. And if we also know that from what we talked about pipes, if we go back to when we were introducing this before, we made the case that the friction factor we can write as this Darcy-Weisbach coefficient. It's just for going around a bend in a pipe. It's just a number. It's a non-dimensionless number because it gives a length as a function of a length. And so that's kind of our equivalent of this loss here. And so we can write that loss as a function of this shear stress that acts on the base of this. And if we equate these two equations to each other, we end up ending with a v squared term, and by dealing with that v squared term, we can just rearrange it, and we end up with this final relationship. So you don't need to know the derivation, just need to know the endpoint that we get to, and that is that we have a coefficient. This is density times gravity. This is density, so it's a function of gravity only. This comes from the 2 in the v squared over 2g. This is some kind of loss coefficient, which says how much head loss as we get downstream. If it's a big number, we're getting a lot of head loss as we go downstream. If it's a little number, we're getting little. And so we have this as a coefficient that goes outside, and it's a function of hydraulic radius times the gradient of our bed. Take square root of it from this term here, and we end up with the velocity. And so this, if we then manipulate it, this coefficient we have to parameterize in some way. It doesn't really matter what it is. It turns out that this coefficient is related to the hydraulic radius to the power 1 over 6. And so if we have hydraulic radius to the power 1 over 2 or 3 over 6, when we combine them, we get something to the power 2 over 3. Right? So this is 3 over 6 plus 1 over 6 is 4 over 6, which is 2 over 3, which is where this comes from. And so all we need to know is that we end up with these two expressions. And they give us an average flow velocity down our channel. And I suppose that's not what I wanted. This is what I wanted. Gives this. They give us an average flow velocity v bar, which is a function of, didn't want to do that. And this is perimeter area, velocity, length downstream. I guess it doesn't come into these equations because it's coming this. And I guess we just need to know that S0 is equal to delta Tz over L That's it. And I suppose the other remaining thing is that the volumetric flow rate is just equal to the average flow velocity times the cross-sectional area flow, which is what this is. And so the only things to remember are that this coefficient kappa changes from SI units. We'll try and use SI all the time. It's just equal to 1. Has no, it is dimensional, so it matters what the units are that you use in this. So this is non-dimensional, a length per unit length. This is going to be in units of length. So it matters that you use meters, and it matters that the result comes out in meters per second. N is this dimensionless coefficient, Manning coefficient, which is really kind of the same as friction factor, which we never see as a graph, but would look like this if the graph was there, just like a friction factor is. But because we're always turbulent, we always see this just as a table. And so we'll talk about that. And so if we want to solve for any problem, then we just use exactly that. So we know that this is either 1 or 1.49. We figure out what the hydraulic radius is for our system, and the hydraulic radius is just equal to the area of flow divided by the perimeter, which we have here, and the gradient, and everything else just falls out. And so to solve problems, then we can solve them in a variety of different ways. The value of the Manning coefficient, lowercase n, changes from being for smooth channels, a small number, to flowing through channels with lots of trees in it, a bigger number. And so those would be the values of the friction factor that are stacked up on top of each other on this kind of Moody diagram. So depending on what the flow is through, we can get a value of n. We don't care about Reynolds number because for all values we think we'll be turbulent. If we're looking at flow within a wide channel, sometimes we can get away with using the approximation that the hydraulic radius is actually equal to the width of the channel. And we can show that to ourselves just by realizing that since hydraulic radius is the area over the perimeter, as the width gets very wide, then the cross-sectional area essentially just comes the width times the height. And these little heights on the edge don't make any difference. The main drag is just due to the drag on the base of the bed. So if it's 10 times wider than the depth, then you can get away with using this approximation. And if you have a channel which is non-uniform, then you can get away by using it in segmented form. So you could calculate the flow rate through this whole channel just by dividing it up into the individual components. And so you'd get the flow rate as being the flow rate in area 1, which would be Q1, and Q2, and Q3. But you just have to remember that in doing this, these of course could have different values of the n, the Manning coefficient if you wanted, or not. But I guess the only thing that you have to remember is that when you're calculating the hydraulic radius for this, is that the hydraulic radius is the flow area which is given by this segmented portion here. So the flow area for 1 would be this full area here, but the perimeter is only the wetted perimeter. And so you have to be careful that the wetted perimeter is just going to be this length here plus this length here. And the reason for that is that obviously this perimeter here is flowing down the stream at some velocity v1, but it's also going at the same velocity v2 in the compartment that's next door to it. And so the wetted perimeter, this is the wetted perimeter. So you should think of this as the wetted perimeter. So I think that probably makes sense. What else can you do with these when we finish it off? We won't get to an example. Maybe we'll do that next time. The other things that we could do, I suppose, would be that if we want to think about the most efficient section, then the most efficient section would be the one where it has the minimum drag applied on it. And the drag force that we apply is going to be the shear stress, which is a function of the velocity and the Manning coefficient, and the wetted perimeter and the length of which it occurs. So this is a function of an invariant coefficient, Manning coefficient. The length over which it goes is the same in each case, so the only thing that we can control is the wetted perimeter. And so if you wanted to maximize the flows within a section, what you'd want to do is minimize the wetted perimeter. And we know that the hydraulic radius is equal to the area divided by the wetted perimeter. And so if you're minimizing the perimeter, then you're maximizing the hydraulic radius. And so in this expression, you want to maximize the hydraulic radius. And so if you look at rectangular sections or triangular sections or circular sections or trapezoidal sections, then you get the maximum flows when you maximize the hydraulic radius, and that happens to be when the rectangular area, when the depth is equal to half the width, or when it's a triangular section that has a right angle in it, when it's a circular section which is half full, not quarter full, but half the radius full, and in a hexagonal section which is 60 degrees, and where the slope length is exactly the same as the wetted base. So those are the most efficient sections to travel in. And I see we're right up at time, so maybe we'll save that for next time. So that's it. So we've tried to put it in context of pipe flow, external flows, now open channel flows, have an extra degree of freedom, so we have to figure out exactly what the height is, which is kind of a free parameter, and so we have to approach it slightly differently. But the basic mechanics of what's going on is the same, is that you're getting something driving flow, which would be either pressure in pipe flow, pressure in external flows, or gravity in case of these other flows, and we're balancing that against the losses we get by drag on the base of the flow. And so these are the easiest ones. This is Manning. So this is the question that is not on your final, but the question that might be on your final we'll talk about next time. So again, for those who came later, apologize that we have back-to-back tests. It just worked out that way because I was using the testing center. Next week is pipe flow networks, external flows, and open channel flows. And there's a question on each of them. The stuff is posted for the review session as well, so you can look at that and take that as your guide in all of these. Welcome back.